Mesdames, Messieurs, bonsoir, bienvenue. Bienvenue à cette première soirée, cette première conférence du Colloque Wright pour la science, dont c'est la 20e édition cette année. C'est un immense plaisir, vous imaginez bien, de vous retrouver si nombreux ce soir. Il y a 2 ans, l'édition a été un petit peu chahutée. La scène était la même, mais la salle était vide. Tout le monde était bien sûr en ligne. On a fait avec les moyens du bord à l'époque, mais on a eu un excellent colloque. Mais on est évidemment tous très contents de vous retrouver tous ce soir ici avec nous. Et bien sûr, bienvenue aussi à toutes les personnes qui nous suivent en ligne sur les réseaux sociaux. Mon nom est Olivier Dessibourg, je suis journaliste scientifique et c'est moi qui aurai le plaisir, le privilège, l'honneur de vous accompagner durant ces 5 soirées cette semaine pour la modération des discussions. Comme à chaque édition du Colloque Wright, nous avons le privilège, vous le savez, d'accueillir des orateurs de renom venant du monde entier. Cette année, bien sûr, ne fera pas exception et tous vont nous faire voyager avec eux à travers, et ce soir même dans la Terre, puisque, vous le savez, le thème choisi cette année pour le colloque, c'est les 5 éléments. Je vous en reparlerai dans un instant. Mais avant d'entrer dans le vif du sujet, j'aimerais passer rapidement la parole à 2 personnes pour quelques mots de bienvenue. La première est le recteur de l'Université de Genève qui nous accueille en ces lieux, Yves Flukiger, que je cherche du regard, qui est ici. Bienvenue.
Monsieur le Président de la Fondation Wright, chers collègues, chers amis de la Fondation Wright, c'est pour l'Université de Genève un immense privilège de pouvoir vous accueillir en cette salle, comme tous les 2 ans, pour cette conférence qui nous permet effectivement de pouvoir présenter à un grand public les thématiques les plus avancées dans le domaine de la science. C'est une fonction extrêmement importante de la Fondation Wright qui nous tient aussi beaucoup à cœur, puisque une de nos missions, évidemment, dans nos relations avec la cité, est particulièrement de pouvoir diffuser la connaissance scientifique, de pouvoir la rendre plus accessible à un grand public. Et c'est pour nous, évidemment, un immense privilège de pouvoir avoir ces 5 conférenciers qui vont nous entretenir au cours de cette semaine sur les 5 éléments fondamentaux. C'est effectivement quelque chose qui est plus que jamais indispensable de nos temps où le public, la société attend évidemment des réponses des experts que vous êtes, que nous sommes, par rapport à toute une série de questions que la société se pose. Ce rôle-là est de plus en plus important pour notre université et c'est la raison pour laquelle je suis très reconnaissant à la Fondation Wright de pouvoir organiser ces événements toutes les 2 années en attirant à Genève des conférenciers de renom. Il a été dit effectivement tout à l'heure, on va parler cette semaine de nous-mêmes, de la Terre, en évoquant effectivement ces 5 éléments fondamentaux, en commençant aujourd'hui par la Terre. Et je suis certain que durant ces 5 journées, 5 soirées de conférences, vous aurez l'occasion de venir participer avec nous à ce colloque, ce 20e colloque de la Fondation Wright, et de pouvoir poser toutes les questions aux conférenciers qui sont ce soir présents dès le premier soir. Et je crois que c'est aussi un événement un peu particulier de pouvoir avoir des personnes qui vont suivre ces conférences tout au long de cette semaine. Donc je souhaite à toutes et à tous une excellente soirée, d'excellentes conférences à venir pour toute cette semaine. Et je passe sans plus tarder la parole à Thierry Courvoisier, le président de la Fondation Wright. Merci beaucoup de votre présence.
Merci, bonsoir. C'est un plaisir de vous souhaiter la bienvenue pour ce énième colloque Wright. Alors, si le recteur dit que c'est le 20e, on va le croire. Il n'y a aucune raison de douter de ceci. Et on s'en réjouit beaucoup. Et on se réjouit de vous voir nombreux et de vous voir nombreux pendant toute cette semaine. Nous avions envie de parler de notre planète cette année. Pas tellement pour sensibiliser aux misères de notre climat et de la biodiversité. Tous ici sont bien conscients de ces enjeux, mais bien pour raconter quelques-uns des progrès réalisés ces dernières décennies dans la connaissance que nous avons de la Terre. Ces progrès sont multiples et importants. Ils sont apportés par des instruments de mesure sur Terre, sur mer et dans l'espace, et par les interprétations qui sont faites de ces mesures. En prendre connaissance fait partie de notre culture dans le meilleur sens du terme. Nous avons choisi 4 thèmes, chacun lié à un des éléments dits fondamentaux. Un clin d'œil à la très longue tradition de la démarche scientifique, illustrée par la recherche de constituants premiers. Une manière encore de constater qu'observer la nature est la manière de très loin la plus fructueuse que l'humanité ait trouvée pour répondre aux questions que notre environnement nous suggère. Nous savons maintenant que la matière n'est pas faite de mélange d'eau, de terre, de feu bon, anyway, je ne sais pas lequel j'ai oublié, mais ce n'est pas très grave, mais bien d'atomes. La démarche n'en a pas moins porté de multiples fruits au fil des siècles, et elle garde un côté poétique qui n'est pas pour nous déplaire. La vie est aussi une composante marquante de notre environnement. Sa nature et son origine, ici ou ailleurs, restent à élucider. Un beau sujet pour compléter la palette que nous avons voulu vous proposer cette semaine. C'est une vue kaléidoscopique en 5 éclairages, plus qu'une synthèse que nous vous proposons. Chaque élément fondamental servant de prétexte pour analyser un aspect de la planète. Merci donc à nos 5 orateurs de partager avec nous leur savoir. Nous leur sommes très reconnaissants d'avoir pris le temps nécessaire pour être avec nous cette semaine et pour préparer leur contribution. Merci à nos collègues genevois pour les liens qu'ils ont au sein de leur communauté scientifique respective, liens qui nous ont permis de mettre sur pied ce programme, et vous les entendrez présenter nos orateurs chaque soir. Merci à l'université de nous prêter ses locaux et main forte dans l'organisation du colloque. Merci à la société académique de nous avoir rejoints dans notre démarche, tant ici que pour le spectacle qui accompagne ce colloque. Merci encore à tous les acteurs qui rendent cette semaine possible et agréable, les interprètes, les services techniques et de sécurité, Van et Ascension Lozano, infatigables, et Olivier Dessibourg pour l'animation de nos soirées. Ceci dit, je nous souhaite à tous une excellente semaine.
Merci, Monsieur le Recteur. Merci, Monsieur le Président de la Fondation Wright. Vous l'avez compris, ce qu'on vous propose cette semaine, ce n'est pas une vue panoramique de tout ce qui constitue les géosciences, mais vraiment 5 plongées particulières dans les recherches de 5 scientifiques de renom, ou plutôt 4, si je peux dire, en tout cas pour les géosciences, entre lundi et jeudi. On parlera des 4 éléments. Tu as oublié l'air tout à l'heure. Voilà. La terre, le feu et l'eau, c'est moi qui ai oublié le dernier. Et vendredi, effectivement, le 5e élément qui a été rajouté par la suite, vous le savez bien, la vie. Cher à Luc Besson, qui en a fait un magnifique film, il y a tout juste un quart de siècle. Ceux et celles qui viendront tous les soirs de cette semaine verraient que, à la fois dans l'Antiquité, ces 5 éléments étaient liés, et aujourd'hui, bien sûr, les domaines de recherche qu'on va traiter sont bien sûr aussi interconnectés comme jamais. C'est pour cette raison, et cela a été dit, qu'on a la chance cette année d'avoir quasiment tous les conférenciers tous les soirs. Alors bien sûr, on ne va pas tous les prendre sur scène, mais on va en prendre un maximum pour avoir des discussions aussi intéressantes que possible, au-delà du sujet de la soirée, mais avec eux tous ensemble. Chaque soirée cette semaine se déroulera donc en 2 parties. D'abord la conférence en elle-même, en anglais la plupart du temps, voire je crois tout le temps. Donc c'est pour ça que vous avez dû ou pu recevoir un casque de traduction simultanée à l'entrée. Et ensuite une partie questions-réponses auxquelles vous pourrez participer, également en ligne, j'y viens dans un instant, en posant vos questions, soit en anglais, soit en français. Et les orateurs sur scène auront le casque pour entendre la traduction en anglais si la question est en français. Donc, n'hésitez pas à poser vos questions, ne soyez pas timide de les poser également en français si c'est nécessaire. Et en ligne également, il est possible d'écrire des questions qui seront relayées ici par quelqu'un dans la salle aux orateurs de ce soir. Ce soir, nous commençons donc par la Terre, avec le privilège d'accueillir Friedhelm von Blanckenburg. Et pour le présenter, vous savez, c'est la tradition du colloque Wright. J'ai le plaisir d'inviter sur scène une personnalité de l'Université de Genève, en l'occurrence ce soir Sébastien Casteltor, professeur au département des sciences de la Terre de la Faculté des sciences de l'Université de Genève. Merci.
Merci Olivier. Bonsoir à toutes et à tous. Nous commençons donc ce soir avec la Terre, comme premier des 5 éléments de cette semaine Wright. Et j'ai donc l'honneur de vous présenter notre premier conférencier, Friedhelm von Blanckenburg, qui dirige la section de géochimie de surface au prestigieux centre allemand de recherche en géosciences de Potsdam. Il est également professeur à l'Université libre de Berlin. Friedhelm est un géologue. Un géologue, c'est un scientifique dont l'objet d'étude principal est notre planète, la Terre. Comprendre son histoire, comprendre son fonctionnement dans le but d'en connaître les ressources, mais aussi d'anticiper les risques naturels que vous connaissez tous, comme ceux associés aux volcans, aux tremblements de terre et au climat. Friedhelm a cette particularité rare qu'il a au cours de sa carrière, en s'appuyant toujours sur des développements méthodologiques à la pointe du domaine de la géochimie isotopique, dont il va parler ce soir, et de la spectrométrie de masse, des termes techniques que j'espère il va vous faire comprendre, toujours produit des avancées scientifiques majeures qui ont vraiment bouleversé notre façon de penser dans plusieurs champs de recherche de la géologie. Je voudrais mentionner d'abord la découverte dans les Alpes, avec son collègue Hugh Davis, du phénomène de slab break-off, selon lequel toute une partie de la plaque tectonique lithosphérique européenne, donc la plaque sur laquelle nous sommes, qui plonge sous la plaque adriatique, donc l'Europe plonge sous la plaque adriatique, cette plaque se serait déchirée et détachée dans le manteau qui est sous elle. Et par un effet de rebond et de remontée du manteau, il a pu montrer que les magmas granitiques qui sont au centre de l'orogène alpin sont d'origine mantélique. Donc la plaque tectonique sur laquelle nous sommes, qui semble si solide, en fait peut parfois se déchirer en tombant dans le manteau. Donc ça, c'est quelque chose qui a changé aussi notre vision du monde. Depuis plus d'une décennie, il est pionnier et leader dans l'utilisation des isotopes cosmogéniques. Ce sont ces atomes qui possèdent un nombre particulier de neutrons et qui sont créés par le bombardement cosmique de haute énergie qui vient impacter notre planète. Et il détecte et trace ces atomes afin de mieux comprendre les processus qui sont actifs à la surface de la planète, notamment ceux qui régulent la température de la planète. Et ça sera au cœur de sa conférence de ce soir. En 2009, il a été nommé membre de l'Académie allemande des sciences. En 2010, il a reçu la prestigieuse médaille Ralph Alger-Bagnol de l'Union européenne des géosciences. En 2015, nommé membre de l'Académie des sciences et des humanités de Berlin-Brandebourg. En 2016, membre de la Société de géochimie européenne. Et en 2018, membre de l'Union géophysique américaine. Je citerai aussi le fait qu'il a reçu cette année une prestigieuse bourse ERC Advanced pour son projet sur les effets de l'altération et de la végétation sur les basaltes et les carbonates, un lien très fort avec les thématiques de capture du CO2. Finalement, au cours de sa carrière, le professeur von Blanckenburg a occupé des postes de recherche à la fois à Cambridge et à Oxford. Il a été nommé professeur de géochimie à l'université de Hanovre avant de prendre son poste actuel au GFZ de Potsdam en 2008. Mais c'est ici en Suisse qu'il a débuté, avec un doctorat à l'ETH de Zurich et une position comme enseignant-chercheur à l'université de Berne de 1997 à 2001. Et malgré la grande affection qu'il porte à la Suisse allemande de ses débuts et à la façon originale dont on y prononce les K et les R, Friedhelm est très heureux de se trouver ce soir invité de l'autre côté du Röstigraben, où nous sommes également très heureux de l'accueillir pour ouvrir ce colloque Wright. Donc je l'invite pour sa conférence. Merci.
Merci. Merci Sébastien pour cette introduction. Merci pour l'invitation à la Fondation Dudley Wright. Et je suis allemand et je m'excuse, je préfère donner cette présentation en anglais, mais j'espère que vous pouvez entendre quand même. Alors, I will talk in English and I will talk about our planet. And it's a special planet. It's blue and it's wonderful. There's life on this planet. It's very delicate, and it has a very, very fragile equilibrium with which it is itself organizing its habitability. And this will be the topic of my talk. In the first part, I will talk about how this equilibrium comes about. In the second part, I will do something which is more complicated. I will talk about the more scientific work we do on one of the periods in Earth's history that is of particular interest. And you can, if you're too tired, you can sleep in that part. And in the third part, you have to wake up, and you will. Then I will be talking about Earth's future, but only briefly. That is not actually the topic of my talk. The topic of my talk is, how does planet Earth regulate itself? So the first question we have to ask is, why is our planet blue? And of course, because there's liquid water on the planet. And the second question we have to ask, why is there life on Earth? And this is because there is liquid water on Earth. And there was almost always, through 4.5 billion of years of Earth history, there was liquid water on this planet. So now we know that liquid water is only possible between 0 and 100 centigrades. And apparently it was never so hot that all water would have been evaporated. And it was never so cold that really all of water has been frozen. Hence, life always survived for since the beginning of life, let's say 3 and something billion years ago. And that is pretty amazing. So there's something that regulates Earth's climate. So let's do a really simple thermal budget. This is a black body, and a black body is only a theoretical concept. It is something, a physical body that absorbs all the irradiation. But of course, this is not how Earth looks like. Earth has white polar caps, and it has clouds. And if we put onto this black body the ice and the clouds, and then we take the heat that comes from the sun, we would end up with a temperature of minus 18 centigrades. So this should really be the temperature of the Earth. But that is not what we have. We have on average about plus 15 centigrades. And I think since you are a very science-interested audience, you all know why we have not minus 18 centigrades, but plus 15 centigrades. And this is because of the natural greenhouse effect. There's just so much CO2 and a few other greenhouse gases, water, methane, in the atmosphere that the temperature is increased from minus 18 to plus 15. So we owe all this to the greenhouse effect. This is basically the solar irradiation is kept on the Earth by reflection and reflection again and again until it's back irradiated into outer space. And for this, we need these few trace molecules in the atmosphere. But we need enough of them to keep the Earth warm, but not too much. And we don't need too little of them, because else the Earth would be frozen. So how does that work? So we have to interact, and we have to ask, so what is the main source of CO2 to the atmosphere? And it's volcanism. I mean, they're all biological cycles, which you read about in the newspaper each day, and fossil fuel burning. I'm not talking about this. I'm talking now Earth history. And in Earth's history, the main and only source of CO2 is volcanism. So deep from the interior, as magmas and volcanoes erupt, and I think we will hear more about this in the talk by Stephen Sparks, CO2 comes about, and it's constantly being emitted to the atmosphere, and also at the mid-ocean ridges. Now, this happens through all of Earth's history, so why didn't CO2 accumulate forever and ever and ever? And then we would have a hothouse hell here, like Venus, where it's like 400 centigrades, and there is likely no life on Venus. And the reason is there's a removal mechanism that more or less removes exactly the same amount of CO2 that volcanoes emit. And this removal mechanism is called weathering. Weathering is the process that transforms rock into soil. So here is a weathering profile, and it's like about 4 meters depth. You see rocks in there. But in between, you see this brown mass that is not soil yet, it is weathered rock. And only at the top, at the very surface layer, you see the very thin, fragile layer of soil. But throughout this profile, CO2 is being consumed. And now we have to do a little bit of chemistry. Sorry for those that don't like chemistry, but it's so simple. What happens in the atmosphere constantly is we put CO2 and water together, and then we have something called carbonic acid. And this acid can decompose rocks. So we put the carbonic acid on a mineral, let's say a mineral calcium silicon oxide. We put 2 carbonic acids on there, and then this mineral decomposes to calcium and to an atom that we call bicarbonate and silicic acid. So now we have consumed CO2, okay, with this reaction. Now, but where does this CO2 go to? And it goes into the ocean. Because if we weather, we put water onto our soils, and this water flows through rivers, and eventually it flows into the sea, and it takes the calcium with it, it takes the bicarbonate with it, and now we bind the calcium and the bicarbonate to form calcium carbonate, and this mineral is also called calcite. And then we release a bit of carbonate also back into seawater, but actually most of this is done by marine organisms, corals, foraminifers, and calcifying organisms. So they lock away the CO2 that volcanoes emit. And now key to all this is that exactly the same amount that volcanoes emit is then, by all this weathering process, is transported to the oceans. I'm not talking about the oceans today, I'm talking about this reactor at the Earth's surface, the weathering zone, because this is where the action takes place. So here we have a whole cycle, and I must apologize that this diagram is in German. So we emit CO2, in the atmosphere we lock it, we combine it to carbonic acid, the carbonic acid rains down to soils, it weathers the soils, and then bicarbonate and calcium is transported to the oceans and is deposited as calcite. So this cycle goes on and on and on, and probably goes on since all of Earth's history. Okay, so far so good. But then, of course, all these things vary. Volcanic emissions vary, the mountains vary, everything in Earth's history always varies, but still there's an equilibrium in here, and this equilibrium is called the feedback. Into this mechanism, there's a feedback built in. A feedback works as follows. Let's assume the Earth for some reason gets too cold. I mean, there are always like geologic reasons why Earth would get too cold. One would be that we have big continents at the poles where ice caps form, and then the albedo, the reflective power of the Earth, increases. Or there could all sorts of various reasons why Earth would all of a sudden, by geologic reasons, get too cold. So if it gets too cold, we have to prevent the Earth from running into an ice world. So what happens if it gets too cold? We have less water evaporation. The atmosphere is colder, the land surface is colder, hence we have less of this weathering reaction. Fewer carbonate sediments form in the oceans. And then CO2, which, because the volcanoes don't care whether the Earth is cold or not, the volcanoes continue to emit. So now CO2 starts to rebuild up in the atmosphere. And then it gets warmer, and the greenhouse, because the greenhouse effect gets warmer. So this is a feedback. Okay? Gets colder, reaction re-equilibration of the reaction, then gets warmer again. Stabilization. It's like a fridge at home, which switches on if you remove a bottle of beer or milk from your fridge. We can do the same thing the other way around. Let's assume it gets too warm, and this could happen if, for example, volcanoes for some reason decide to emit much more CO2, which they do. Then we have, if it's too warm, we have, sorry, this is a mistake. It should say more weathering, because we have more water and more heat. We have more carbonate sediments. We have then less CO2 in the atmosphere because we have more weathering. And then we have a weaker greenhouse effect, so it gets colder again. That's the equilibrium. That's the feedback mechanism. And this has governed Earth's temperature throughout those billions of years. So actually, I could finish my talk now. These were the basics. I hope you could follow up to now. But then all of this is a hypothesis. Actually, we haven't really seen it at work because this just takes hundreds of thousands of years to work and we can't observe it. So how do we test this theory? And this is where geologists are very, very good in. They look back into Earth's history and they reconstruct past climate. Because actually, on the dynamic Earth, even in climate science, there are only two ways to test feedbacks. And one is you do this, you look back into Earth's past and see how feedbacks operated. And the other method, of course, you build a huge, big computer program, and I'm sure we hear this in other talks. this week that then work out these feedbacks by computing them. And we do this in reconstructions of past climate. Now, how do we do that? There's a great program called the Ocean Drilling Program, and what the Ocean Drilling Program does, there's a ship or several ships constantly cruising the oceans, and they drill into the seafloor, and the seafloor is typically covered with sediment. And the sediment mainly is composed of these small little calcite shells, like foraminifers. These are small little organisms that form these calcite shells, and they rain down onto the seafloor, and then you get a layer, it's like a book, the old sediment as the bottom, and then you get younger and younger and younger. The ship drills these cores that we see here, and then the geologists are very good at reconstructing the age with various methods, so they know exactly what the age is of each interval, and then we measure stuff in there. What do we measure? The composition of seawater has varied through time, because the weathering input varies with time, and because climate changes. For all of these reasons, seawater chemistry changes. And now we want to reconstruct Earth's past climate from the sediment from which that was deposited from the seawater. But of course, these foraminifera shells, they consist of calcium carbonate, they don't consist of seawater composition. So we use something in there which are the isotope proxies. So Sébastien has introduced that I'm actually an isotope geochemist and I use mass spectrometers. So this is now most of the remaining talk will be about isotopes now. So these small shells, they contain isotopes. And they tell us a story. Now, here's a movie. What are isotopes? So here's an atom, and there are electrons in yellow. They surround the nucleus of this atom, and there are protons in red, I think, and neutrons in blue, I hope. Let's see whether this is correct. This should be an oxygen atom. If you're fast, you can calculate whether it's right. But it should tell the answer now. So yeah, so there are 8 protons and 10 neutrons. So this is clearly an 18 oxygen atom. So this is an isotope. There's another one that only contains fewer neutrons, and that then would be a 16 oxygen. Now, so here we have the 16 oxygen, which you don't see because you can't count the blue. And now we put them on a balance, and the 10 neutrons are heavier. The one with 10 neutrons are heavier than the 8 neutrons. Actually, this contains a joke. There's a nose on this balance because I had a project which called ISO-NOSE, isotopic sensing of novel isotopes, blah, blah, blah. So there's a nose on here. But in fact, this is a mass spectrometer because it's a balance that weighs isotopes. In fact, these atoms are so small that you can't put them on a balance. So you need something more sophisticated. And here's our real isotope balance, and that is a mass spectrometer, and this is our toy. And all isotope geochemists love mass spectrometers, and they constantly develop them. We have one, I mean, we have many, but this is the one that I mostly talk about in this talk. This is one for stable metal isotope. Oh, sorry, there's something, I did a mistake here. I need to, sorry, this movie just doesn't start. On peut commencer la animation? Ah, no, okay. Merci. So this is Josie, and she has samples, and they are dissolved, and the elements are in these small little beakers, and now there's an automatic sampler, and the sampler gets a given sample that we've told the computer to measure, and then it puts this into a mass spectrometer, which contains a lot of stainless steel and lots of complicated electronics. And back there is a magnet, and the magnet separates the isotopes. And this is a torch, it's a plasma, and it ionizes all this. And this is an animation. So here we see this torch, and now we get all the heavy and the light isotopes. They are ionized, so they contain a charge. They're accelerated through an optical lens, like to 10 kilovolt, and now they run through a magnet, and the magnet separates the light isotopes to the right and the heavy isotopes to the left. And then they end up in collectors, in small little buckets, and these buckets have electronics, which we see here, and they count the buckets. They count the number of isotopes that end up in there. What we do is we always measure ratios. We always measure a ratio of one isotope to the other. So this is the mass spectrometer. So now we get an isotope ratio, and now I'll show you lots of isotope ratios. The most common one used is oxygen 18 to oxygen 16. What happens is they fractionate. When oxygen goes, let's say, from water into rain, it's stupid, from water vapor into rain, more light isotopes would go into rain. If the oxygen goes into the foraminifer, sometimes more heavy light isotopes go into this foraminiferal shell. So there are always these reactions that always change the isotope ratio. And we know what they are, and we can use this to measure them on these foraminiferal shells, for example, to reconstruct Earth's temperature. Now, there are lots of steps in between, which I won't explain, but what we get is something like this. So, what do we see in this diagram? On the x-axis, the horizontal one, on the right we have millions of years, which doesn't say so. I lost the units. So on the right we have 65 million years. On the left we have 0 million years, that is today. And we have all these Earth histories in the so-called tertiary age. On the Y scale, on the right we have oxygen isotope ratios. Don't bother with that. For you, more interesting is the left scale, and says temperature relative to today. So you see at some time in the past it was 12 degrees warmer than today, and in another period it was -4. This is ocean temperature, so don't worry what these actual numbers mean. But what we see is that Earth temperature has clearly fluctuated in the past. So, and there have been events. There were short perturbations, like here in the Paleocene-Eocene thermal maximum. All of a sudden it was much, much hotter, and we still don't really know why. There was the Middle Eocene, it was much hotter, and then the temperature came back. So even without humans, Earth's temperature was perturbed by something that has happened on the Earth, by geology probably, or maybe even by biology, we don't know. So these events happen. And then there was a period in the Oligocene and the Miocene where it was pretty boring, and this is constant. And so in this period, the feedback must have been operating really, really well and really stably for a long period, for several millions of years. And then we have the part that is the one that I'm going to talk about in the next part of his talk. We saw this slow cooling. About beginning 15 million years, the Earth got colder and colder and colder, which led eventually to the formation of the glaciated poles. So before 15 million years, there was neither ice on Antarctica, which began to grow about at that time, about 13 million years. The ice in the northern hemisphere only began to build when it got really cold, 2.5 million years. Since then, we have Greenland glaciated and so forth. So all of a sudden, it got colder. So the thermostat has not been constant. This equilibration by the weathering feedback wasn't running constantly. Something has changed it. Now, the question is what? And we already guess that something must have changed, and this was the CO2 concentration in the atmosphere, because that has the power, as we all know, to heat the atmosphere. And actually, we have means now, since about 10 or 15 years, to reliably reconstruct CO2 in past intervals in Earth history. And what we do is we measure the stable isotopes of boron, 11 boron and 10 boron, in the same shells of foraminifers as we measure oxygen. And now we see CO2 on the right-hand scale. Now, this stippled line there, that is the pre-anthropogenic level. 280 ppm was atmospheric CO2 concentration before humans began to burn fossil fuels. So this is for reference, and we see that for many periods in Earth's history, between 400 million years and, let's say, 50 million years, Earth's temperature was actually warmer than today. Now, we go into the stable period that I have already shown to you, and about 25 million years ago, all of a sudden, we already know that the temperature was stable. It was also colder from the oxygen isotopes, we know this. Earth cooled, and indeed, CO2 dropped in that period. And then we go to today. This is from ice cores now, drilled in Greenland or in Antarctica, and you can measure the actual amount of CO2 atmospheric in the ice, in the bubbles contained in the ice. And we see that CO2 was even still lower, and this is what made the ice ages. So, and then we see in the very last, in the left part of this diagram, we see the incredibly stable period of the Holocene, the last 10,000 years, which led to the development of our modern society. Okay, so CO2 dropped and it got colder. This all makes sense. The feedback is an operation, apparently, and is driven by CO2. But now we have to ask, so why does CO2 change? Okay, so why did the thermostat change, and why did CO2 concentration all of a sudden go down, especially in the last 15 million years? So I will talk about the last 15 million years now. Remember, it got colder and we had less CO2. So why is the question? Now, there are three hypotheses, and I'm not going to talk about all of them because that would be too much. But hypothesis one is there were just fewer volcanic emissions. Now remember, we have a balance. A balance means an equilibrium of what we call fluxes. The balance of atmospheric this is actually, even if you don't notice it, but this is mathematically, this is a differential equation. It's the dCO2 dt. We have volcanic emissions putting CO2 in the atmosphere, and we have weathering sucking CO2 from the atmosphere. And we have totally stable thermostat. On that right-hand equation, volcanic emissions must be equal to weathering withdrawal. And that is actually exactly what the feedback does. Now, if we do have fewer volcanic emissions, then weathering would also be fewer. We would have a lower and different balance, but CO2 concentrations would get lower. Now, we don't know exactly how this worked. We assume that volcanic CO2 emissions are driven by production and subduction of tectonic plates. So at the mid-ocean ridges, we've seen this on this picture, we always have volcanoes. Some of them are submarine. But then if they are being subducted beneath the continents, we have all the nice volcanoes at the Andes and so on, all around the Ring of Fire, all around the Pacific. If we have faster subduction, we have more volcanism, so we assume there's more CO2 emissions. So this would be one hypothesis. So this is the picture here. If we increase both the spreading rates and the volcanism at the subduction zone, we may have more CO2 volcanism. The problem is we don't really have any good knowledge of whether that happened. Up to now, the assumption was that in the last 15 years, these rates were actually pretty constant, but just this year, two papers appeared where one says they have actually increased and the other one says they have decreased. But this is all reconstructing plates, which is not an easy task. And it's not my task because I'm a geochemist. So this could be a possibility, but we still don't know. Okay? Now, the more popular hypothesis is increased rock weathering. And this is actually almost a paradigm in the Earth's surface geochemistry or geomorphology or geology community. And this was proposed in a seminal paper by Maureen Raymond, Bill Ruddiman in 1992. So it's quite a while ago, 30 years ago. Actually, hypothesis had birthday, 30th birthday this year. So the hypothesis goes as follows. Mountains have been rising by tectonic forces. For example, India was colliding with Asia and the Himalayas rose. We know that the Andes rose. At the same time, we know that the Alps, here at your doorstep rose about the same period. Many mountain belts seem to have risen in that period. Whether they really have risen, we still don't know, but the assumption is that at least they eroded faster. Now, this is a very, this was a paradigm, this was around for the last 30 years, they rise. And if you erode more material, you present more rock to the weathering process. Because if we put here, you have glaciers on top, and you have rivers, and the rivers, they grind down the rock material. You have a lot of surface where soils from. These soils erode very fast. And then you have lots of surface of minerals that can react with the carbonic acid in the atmosphere and weather. So the hypothesis is that this tectonic movement has increased weathering fluxes. Right? So, up to 10 years ago, everybody believed this hypothesis: uplift, erosion of weathering, and then you decrease. But there's a huge problem with this hypothesis, and the problem is there's only so little CO2 in the atmosphere. Remember, we are only talking about something between 300 parts per million and maybe 2,000 parts per million in the past. So that is a very small amount. So if you increase with weathering process by too much, you suck all the CO2 from the atmosphere and there's nothing left. And this would have happened if this would have been done. Within 1 million years, we would have had no CO2 left. So these authors, they totally realized this, but they then invoked that something else happens, like just now for the experts, you also erode organic-rich sediment, they oxidize, and then they also add CO2 to the atmosphere, so there's a compensating process. This is all very complicated, and now the geologists are beginning to question this hypothesis, amongst them myself. But this is a huge, big debate that is taking place. It's still taking place. It's almost getting accelerating at the moment. And here's hypothesis number 3, and this is my preferred hypothesis. An increase in the reactivity of the land surface. Now, this sounds very chemical, but it's simpler than you think it is. Just to put this into, I'll first explain the chemical version of this. So we have something called K here, and it's a reaction rate constant and has the unit 1/time. You just multiply K with the amount of CO2 in the atmosphere, and this dictates how much CO2 is withdrawn. So the flux, essentially. So if K is constant, you have a lot of CO2, you withdraw a lot of CO2. If you increase K, and you have always the same amount of CO2, then you also withdraw a lot of CO2. So now you have two things with which you can play. You can play with K. It's something like a decay constant in radioactivity, the same concept. So the multiplication of K with CO2 concentration in the atmosphere is the rate at which volcanic emission fluxes are being balanced. Now, K is an index for the weatherability. So what does weatherability or land surface reactivity mean? There are two diagrams here. On the left one, we see something in warm climate. This would be a weathering zone like in the tropics, for example, today, where there are no minerals left. So we see these brown, these are the nice little juicy spots that carbonic acid likes to attack the rock or mineral fragments. On the left, they are all gone. K is low, and now we have a lot of CO2 in the atmosphere. On the right diagram, we have a cool climate. There are lots of mineral fragments remaining. They can all react. So K, the reaction rate constant, is high. It's a high land surface reactivity, and now CO2 is lower. Just for the real chemical experts amongst us, you don't need to understand this. You see by the size of these arrows that in both cases, the weathering fluxes are the same. Because K is always inversely proportional to CO2 concentration. So by changing K, you can reduce CO2, but remain a constant weathering flux. Okay? So far, so good. I know this was complicated. You don't have to understand this. Anyway, it's a hypothesis. Okay, but we need to test it. Again, we use isotope proxies. Now I'm presenting you 4 different isotope systems. We've seen this one already. This is the oxygen isotopes. They have decreased, and it got colder. About 5 centigrades, it got colder between 15 million years ago and on the average Holocene, or in the Holocene, okay? So you've seen this already. These are the oxygen isotopes in forams. We've seen this already. It's just a different diagram. These are the boron isotopes. And we see that atmospheric CO2 has also decreased from about 500 parts per million 15 million years ago to about 300 parts per million pre-anthropogenic. So that makes sense. We saw this already. And it's compatible with all of these hypotheses, actually. But now we have yet another isotope system. Also, here, CO2 decreased. Yeah, okay. But now we have another isotope system, and this I won't explain to you, because it's just too much and too complicated. But in a nutshell, we have an isotope, beryllium-10, which is cosmogenic and is produced in the atmosphere, and it rains down, especially into the ocean, at a constant rate, about 1 million atoms per year per square centimeter. This is a very rare isotope, but it flux, it's known as our clock. And the 9 beryllium is a stable isotope that goes into the oceans from weathering. From weathering of rocks. It's a trace element in rocks. Now, if the weathering rate goes up, and the 10, then the 9, there's more input of 9 beryllium into the oceans, but the 10 beryllium is always constant, and then this ratio should go down. And we have measured this, corrected it for radioactive decay, because 10 beryllium is radioactive, and we have a constant ratio. Hence, our hypothesis is that the weathering flux was constant. There was no increase in weathering flux as proposed by this Himalayan uplift hypothesis. Okay, now this is disputed, and this is a little bit of inside geochemical stuff. I mean, geochemists always believe the hypothesis of the proxy they use. So everybody has a favorite proxy. This is my favorite proxy because we developed it, so I believe in this hypothesis. Others use another isotope system, for example, strontium 87 to 86. This gives you different results, so they come to a different scientific conclusion. This is how science works, especially the Earth where you haven't been around. So actually, you have to believe in one piece of the evidence if it's contradicting. And this is where we are. But now the question is, we still don't know why CO2 decreased while weathering flux was constant. Now remember, I had this hypothesis 3, the land surface reactivity increased. And here's, so just go back. The beryllium shows us the weathering rate could have been constant, but here's another isotope system, and these are the stable isotopes of lithium. Lithium 7 to 6, they are all being released by weathering. And then the lithium goes into the oceans, and then the same foraminiferal shells, they also get the lithium. And if the reactivity of the land surface goes up, then the rivers have a higher 7 to 6 lithium ratio. This is stable isotope fractionation, too complicated, but that is actually a fact. If the land surface is more reactive, meaning we have more minerals there that can still weather, then this isotope ratio goes up. And indeed, in the last 15 million years, there was an always higher and higher isotope ratio of lithium delivered into the oceans, meaning land surface could have gotten more reactive. Now to put this whole thing together, the whole story, in the last 15 million years, it got cooler by 5 degrees. There was less CO2 in the atmosphere. There's a mistake here again in my labeling when I translated all this from German into English. The third one should be doubling of the land surface reactivity, lithium isotopes, and the fourth one shows constant weathering flux. So this is all one internally consistent picture, which is compatible with hypothesis 3. Whether hypothesis 3 actually really works still depends on whether you believe that these isotopes systems tell us what I'm telling you about them. So it remains a hypothesis because it depends on these isotope systems. Okay. Now, what happened? Well, we have to put a bit more reality into this now. We were talking, so what actually sets this K? And I've shown you these images here. the land surface with a low reactivity and with a high reactivity. And how would this look in reality? In reality, it would look like this, for example. Here to the left, we see a tropical soil. This is actually in Sri Lanka. There's a very deep, I mean, the rock is weathered to 10 meters depth. There's almost no rock left. It's all consumed by weathering. On the right, we see something from the Chilean mountains in Chile, in South America, and there's lots of rock left. So the weathering profile on the left would have been low weatherability, and the one to the right would be high weatherability. So what this means is that in the last 15 million years, the whole Earth's surface shifted from the state with low weatherability to one with high weatherability, or at least parts of the land surface. Okay? Now there are many, I made my life here simple. What caused this change in reactivity? And I'm just giving you, we still don't know. Well, many hypotheses are around. Still, it could be rifting, it could be production of glacial debris from glaciers, it could be more basalts or mafic rock in tropical areas. So there are lots of hypotheses, and researchers are intensely researching this, and I'm making it simple and just saying we still don't know. It could be a modest degree of uplift in the mountains, and maybe a twofold increase in erosion rate with a small little increase in weathering rate could also work. Okay. But this is what Earth's surface would have done in the last 15 million years to re-equilibrate Earth's thermostat. So a land surface change induced the cooling of the Earth in the last 15 million years. Okay. Now this was pretty exhausting for you, I assume. And before I come to the final part of my talk, I first need to drink some water. And then I want to show you a movie, which is an illustration of the feedback mechanism. It's a tango. So here's one, let's say the man is the solid earth and the woman is the atmosphere. And they're both equilibrated. They dance in a rhythm, very harmoniously. They really coincide with their movements. It's a dance of equilibrium. So the feedback is in operation here, and it's stable. They influence each other, but they keep each other. Now we have a perturbation. This could be an earthquake. It could be volcanic eruptions, big landslides, movement of plates. And now, what happens is that the woman, is pulling him, the atmosphere is pulling the Earth back into equilibrium, and now they dance again in the same stable equilibrium as before. That is the feedback mechanism at work. Actually, dancers really feedback with each other, as you probably know, those of you that dance. Okay, and after this small little entertainment piece, I will come to the slightly depressing part of my talk, which, however, should not be central to what you remember. Central to what you remember should be this wonderful way in which the Earth regulates its own climate, even without humans. It allows for shifts. The shifts have geologic reasons, but they always keep Earth's system in a habitable and nice way so that the Earth always is blue. A wonderful planet. Now, and then humans came and they industrialized. And we need to talk about this because it's just so important. Oh, please don't remember, it's so... Remember the first part of this talk and not this last part. So actually there, just a little background, I have cheated a bit because there are 3 CO2 cycles on Earth. The one is the one with the yellow, you see here this yellow rectangle, that is the volcanism and weathering cycle, and this is only 0.1 billion tons of carbon per year. It's actually very small, the volcanic emissions. We have a much bigger one. This is the organic cycle. of which 60 billion tons go into the terrestrial biosphere and 90 billion tons go into the ocean biosphere. So mainly growth of marine algae. So actually 150 billion tons together go into the organic, are sucked out from atmosphere by organisms growing, higher plants and marine organisms. Now you will ask, so where does all this carbon come from? And actually it's over short time scales, it's a closed cycle. So this organic carbon that forms is also oxidized, as we say. So it's like it's being reacted with oxygen, and then the CO2 goes back into the atmosphere. So actually the same 150 billion tons that go down into the biosphere, they also go back into the atmosphere each year. So that system is sort of in equilibrium, unless geologically we have times also in periods where you deposit organic carbon into sedimentary basins and then you form oil or coal or gas. This does happen, but at on the short term that we look now in the last like decades or so, this was a balance. So this inorganic cycle is the one we have been talking about, which is really small, but this is the one that is really governing Earth's climate over the long term, these 0.1 billion tons, because the other ones are just recycling, they're zero budget, more or less. Okay, but now we have another one. And since about year 1900 or so, but really since year 1950, humans are adding another 10 billion tons of carbon per year to the atmosphere. The 10 billion, this is a substantial fraction even of our organic cycle, but it's even like 100 times more than the volcanic emissions. So this is a huge cycle that humans are inducing. So now, fortunately, our biosphere is absorbing a part of this, but not all of this. As we all know, a substantial part of this, about 10–20% or so, is accumulating in the atmosphere. So now we have these anthropogenic emissions, and that is a big additional flux here, these 10, which is just substantial in comparison to all the natural fluxes. So if we now look at this diagram, and you've seen this already, we've seen on the right, this is the diagram since 400 million years, and it looks a bit strange because these are all logarithmic scales that differ in each of these boxes. So CO2 has come down from 2,000 ppm 400 million years ago to about 1,000 ppm 50 million years ago to 500 ppm 20 million years ago and to 300 ppm in the last 2.5 million years ago. And now, on the left-hand side today, you see these four different paths, and these are the representative concentration pathways of the International Panel of Climate Change. And these are different mechanisms, different emitting scenarios, and you see that if we don't get our act together, CO2 concentration may rise up to as much as 2,000 ppm, a concentration that we haven't seen since 100 million years. At the moment, we're heading to something more like RCP 4.5, so we might see even 600 ppm if we don't slowly begin to act responsibly, which is still a concentration that we haven't seen since 20 or 25 million years. So it's very urgent that we really get onto a trajectory that actually goes back down, like the one seen in blue. Now, at the moment, it doesn't look as if this doesn't happen. And here is, and this is my last scientific slide, coming back to the first part of my talk, this is climate scientists have done an experiment, or this was actually a computer climate model, where they assume humans burn all the fossil fuel that is extractable, like the stuff that is easy to get. And they put it all into the atmosphere. And we may end up with a concentration of, let's say, 1,000 or 1,000 ppm. And then it would take 300 years to absorb. The question now is, how long does it take for the Earth to, because we know that all these feedbacks are in operation, to remove that CO2 from the atmosphere without man doing this? And we see that it would take about 300 years. There's a lot of absorption of CO2 into seawater. So we get back down to something like 700 ppm. Then the CO2 will react with calcium carbonate. This is a fast chemical reaction on the land surface. And then we might get to something back to like 500 ppm. But in the end, the so-called silicate weathering, so the weathering cycle that I've been talking about today, will kick in. But we know it's very small. I mean, the amount is only 0.1 tons, billion tons of CO2. And then it will take 400,000 years to bring CO2 concentration back to pre-anthropogenic levels if we burn all our fossil fuel. And I personally find this shocking. I mean, this is something we rarely hear about, that the perturbation we induce might take a few hundred thousand years to clean up by all the feedback mechanisms that Earth has on scale. So we're actually introducing a huge perturbation into the Earth system where all the feedback mechanisms are knocked out. They just simply can't respond that fast. And this is the timescale we are talking about. And this is something we should memorize if we make political decisions on how we want to do our human future on this planet. Yeah, we should stop that experiment immediately, is my personal opinion when I look at that figure. Yeah, and with this, I'm at the end of this talk. So we've seen how wonderful this planet is to regulate its climate with all these feedbacks on the land surface. It's a wonderful mechanism, and it's a wonderful study object for us geochemists and geoscientists. And if anybody wants to see where all these movies came from, here they are. They're all on YouTube. And each time I do a big research project, I raise money to do a movie. And here you can download them. Okay, thank you very much for your attention.
Thank you very much, Mr. von Blanckenburg, for this nice lecture. Please take a seat. Which one you choose? Not the last one, because that's mine, but you choose. And as said, I have the great pleasure now to invite three of the other speakers of this Colloque Wright pour la Science this week to come on stage, and I'll present you when they are on stage. So I call Kim Prather, Stephen Sparks, and Ilke Furr for the discussion tonight. Go into the middle.
Okay.
Donc, comme je vous l'ai dit tout à l'heure, n'hésitez pas aussi à poser vos questions en français. Tous les orateurs ont un casque et pourront entendre la traduction en anglais. So I'll switch back now to English. I'll ask one or two questions to Mr. von Blanckenburg and then also to the other speakers, and then open the floor to you. So don't hesitate to prepare your questions. Maybe first question to you, Mr. von Blanckenburg. So we have seen, if I sum it up really shortly, we have two processes. One is the volcanoes, and we'll talk about this in a second. The second one is weathering, that keeps this thermostat of the Earth in equilibrium. And actually, in this great article that I recommend to all of you who want to read back what Mr. von Blanckenburg told us, was published both in French, German, and English, because that's a journal that do translation. So it's Pour la Science in French, Pour la Science en français, Scientific American in English, and Spektrum.
Only German.
Okay, so Spektrum der Wissenschaft of Dutch, and Pour la Science in French. In April this year in French. You mentioned briefly Mars and Venus, but why this process of weathering versus volcanoes have not created a similar equilibrium on Mars, for example? We know there are volcanoes on Mars.
Which microphone are we using? This one here?
Yeah.
Okay. There's no water on Mars anymore, at the moment at least. So you need water to do this. And because water from Mars has disappeared long ago, probably 3 billion years ago or so, there is no water anymore, and since Mars has no thermostat anymore.
So that's the only reason? Maybe the distance to the sun as well? Or doesn't
Sorry?
take any... The distance to the sun?
Well, not necessarily, because the thermostat, even in a long distance from the sun, would just equilibrate at a lower level, or could mean, because it would be colder, more CO2 could accumulate in Mars' atmosphere because it's simply colder, not so much weathering, and then you would still have the same, even though the solar radiation is lower.
And my second precision question is about those three hypotheses. So we understood you're in favor of number 3.
Yeah.
We'll hear about the volcanologist in a second, about number 1 maybe. I'll ask you to comment on that. What are the implications? Why is that so important to determine what really happened? And if that's your, call it your hypothesis, what would be the implications?
Well, first of all, this is a basic science question. I mean, it's curiosity. We are Earth scientists. We want to know, why did Earth get colder? That's probably the best answer I can give. I mean, if you're a geologist, it's not so trivial. You're a curious geologist. You are interested to know why all of a sudden it gets colder and we have ice caps on the North Pole and on Antarctica. We want to know this. It's curiosity. That's why it's important. At the same time, we learn a lot about how the Earth's surface works, which has implications for our future.
So we'll come back to this. But let me turn now to the other speakers. So Stephen Sparks, you will be talking tomorrow about volcanoes. The first hypothesis was about volcano. What are your reactions to that?
Well, it was a fascinating lecture.
You need a mic?
Yes, a fascinating lecture, and I think it highlighted the way in which the Earth isn't a simple system. As Friedhelm said, after you either warm it or cool it, and you change it, it can take an awful long time to adjust, to get back to the equilibrium. Perhaps just give you one example, is that when at the end of the last ice age, probably around between 20 and 10,000 years ago, when a lot of the ice caps melted, that actually had an effect of creating more volcanism. It's now quite well documented that after the ice caps went away, Iceland started to erupt more, and that's because the inside of the Earth was changed by the unloading of the ice, and this actually triggered more melting and more carbon dioxide, and it had a feedback mechanism, just like Friedhelm had mentioned, that the volcanoes produced more CO2, so it warmed and we went into a warm period. So we get these cycles all the time on all sorts of time scales, and I think the sobering point really came at the end of Friedhelm's mention is there are so many of these interactions and feedbacks. It's really quite hard to know how they're going to interact in the future. I think what we can say from the past is that it takes the Earth quite a long time to adjust back to where it should be.
Kim Prather, we'll be hearing about your work on Thursday on the oceans, just like as Ilke, but rather on the, let's say, aerosols coming from the oceans, right? So question to both of you, how does your work relate to what Mr. von Blanckenburg has said?
Well, yeah, so I think about feedbacks a lot, but my time scales of the ocean atmosphere are much shorter, right? And so I was fascinated. I really enjoyed your talk. But I also study reactions on dirt in the air. And so I'm just curious, dust. I'm just curious, so when how do you separate, this is just a curiosity question, but an important one, but you showed that the weathering increased by like a factor of 2, right? The weathering rate. Is that because can you distinguish between whether that is just more surface available, more surface sites available, or you could, if you had we know that different soil, different parts of the Earth are more reactive or less reactive. So can you distinguish those, or you get one value that it's double, but do people know what you have, more sites or more reactive sites or both?
Well, actually, I actually said the weathering rate did not increase. It was constant, but the reactivity increased.
That's what I meant. Yeah. So, the rate increased, well, the overall rate. Okay, I see what you're saying.
And that would be that the Earth offers some different land surface to climate to react differently. And like one of the ideas is that there are all these Indonesian islands that are also composed of nice volcanic rocks that like to weather. They also have lots of calcium and magnesium that sucks CO2 from, and they were formed in that period, the Indonesian arcs. So that would be one of the explanations.
And then real quick on this same topic. So one other option, I was looking at your time scales of how long it would take. The ocean, people are looking at geoengineering approaches, which I'll mention a little bit on Thursday. They're thinking about ways to increase or change these feedbacks. But another one is if you think about the uptake by soil itself or dirt itself, right? There's certain fast ways like through agriculture. That wasn't on your time scales. Those would be faster, right?
Much faster, and on the time scales we are looking at, they would also be zero balance. I mean, because all the organic carbon that is formed is over those time scales is oxidized at the same rate in soil. Yeah. Okay. So it doesn't really go into the balance.
Okay, just averages out.
Yeah, exactly.
Ilker Fer is a professor of physical oceanography in Norway, and he studies the reasons why there are currents in the oceans, and he will explain that on Wednesday. Are there any direct link to your work?
Yeah, thank you for an amazing talk. I was impressed by. It just shows how delicate balance our Earth system is.
Bring it closer.
Yeah. And I can draw many analogies, but I was impressed by this K coefficient, and it reminded me of if you look at the air-sea exchange, like the CO2 fluxes, like the piston velocity, the vertical velocity of exchange. Then I thought, could there be an analogy in this budget where you explain the CO2 fluxes that goes with that coefficient, and what determines that? So you called it reactability? Or?
Yeah.
Mm-hmm. So I'm guessing you showed two pictures. One had much more rocks than the other one. So it appears to be like the surface area of the rocks.
Exactly.
Could someone maybe should take into account the total area of this to quantify that? It would be very, very difficult, I believe.
Yeah, that's exactly that. You have to provide a lot of surface area to react with atmospheric CO2. And the more surface area you have, the higher your K coefficient will be. Mm-hmm. But it would also be higher if there's a mineral that is easier to dissolve or has more calcium and so on. So there are many factors that, and actually climate itself goes in one way into K. If there's more water, all of a sudden, somewhere K would also be higher. Let's say we have an area where all of a sudden there's more precipitation and hence more weathering, then K would also be higher. So K is a basket coefficient. It has a lot of things in there that it could do. Yeah, that's right.
So it's time now to open for questions. I ask also for some light in the room. And for a start, we have a question, I think, online, if that's correct.
Yes. Je ne sais pas si ça... Ouais. Si on m'entend. Friedhelm, j'ai une question en français de la part de Dorota sur le chat qui demande si les processus d'altération dont vous avez parlé pourraient être accélérés par l'homme pour en faire une solution au changement climatique. So, could enhanced weathering be a possible solution to climate change, basically?
Yeah, thank you. Yeah, that is a totally relevant question. Indeed, there are about 6 big methods discussed in the climate community with which one can withdraw man-made CO2 from the atmosphere, and so-called enhanced weathering is one of them. What this means is one needs to put powder, rock powder, onto soils. And especially basalt powder. So basalt is a black rock it's a volcanic rock that contains lots of calcium and magnesium, and you need to grind this down to very, very fine grain size, because we're talking about reaction rate constant K, so you get a high K, and then you spray this onto croplands, for example, where you do agriculture anyway. You also add potassium, phosphorus at the same time. It's a fertilizer. The clay minerals that form provide water retention capacity, so there could be positive by-effects. The negative ones is that you may add more toxic metals like nickel or copper or so. But actually, there are numbers that up to 1 to 3 billion tons can be sucked down from the atmosphere. However, nobody has so far shown that it can actually work. So it's a total fiction. I mean, in theory, it would work. Whether we can in practice do it and whether it really works the way we want to, plus we need to grind all this basalt powder, which only makes sense if we do the grinding not with fossil fuels but with renewable energy, which so far we don't have. So it is a process for the future that may save us in a few decades, actually, but so far we are not there yet.
So we're touching on so-called geoengineering here, right? And I'm sure you have comments on that. But maybe my questions to you all is, I mean, some scientists say we don't even have to touch that because once we do that, it's like a foot in the door, and maybe we find a solution, and finding the solution, we will use that solution, and this will prevent us from doing efforts on reducing CO2 emissions. So how do you answer that question? Should we do the research to, the fundamental basic research to test that method or not?
Okay. Yeah, I get asked about this a lot because of the opportunity to potentially use sea spray to seed clouds. And I'll touch on this on Thursday. Yep. And oftentimes, and I also think about seeding clouds to extract water for precipitation. These are all things that are being studied right now. And the pushback that we get is we should not mess with Mother Nature. She's got it figured out. It's all balanced. Don't mess with Mother Nature. My answer? We already are. We're already messing with Mother Nature. We're already redistributing where the water falls and how much it falls, and we're already changing the balances, ourselves. So I feel that, I'm not a strong proponent of geoengineering, but I am a believer that we should understand the things that are involved and how they work so that we have plan B in our back pocket. If things continue to get much worse, we may have no other choice. So we certainly wanted to understand all of these things better than we do right now. So I think it's really important for the research to go on. And again, this pushback about don't mess with Mother Nature, I mean, that train has left the station. Does anyone else want to comment?
Yeah. Well, but I don't know whether you agree with this notion, but in all the community or the academic reports I read, actually the enhanced weathering or other so-called nature-based solutions to withdraw CO2 from the atmosphere are not even counted as geoengineering. Well, it's a bit of a terminology question, but the big fundamental difference is you just enhance a process that nature does anyway, but in a very slow manner. I mean, because there's a weathering feedback, you even doing enhanced weathering won't just. I mean, it will still work within a stable equilibrium, the same as this other method of enriching soil to great depth with organic carbon. The third one is to put this biochar, I mean, coal into soils. And these are all like nature-based solutions, and typically they don't count as geoengineering in contrast to the ones you mentioned, putting aerosols into the stratosphere and sea ice and all these crazy things, which are really could at short term cause big implications. Timescales. Yeah, timescales are different, yeah.
Stephen, you had a comment?
Yes, I'd just like to really just pose an issue which occurred to me while I listened to your talk, which is the very striking difference between the amount of CO2 cycled through the biosphere, 160 billion, I think, compared to the balance you discussed, which was of weathering versus volcanoes. And it just occurred to me, one of the main things we're doing, of course, on the planet is we're reducing the biosphere, biodiversity, we're reducing the capacity of the biosphere. And over the 50 million years, you would have had evolution, perhaps organisms adapting, being more efficient at using carbon dioxide, for example. I just wonder whether we're, at the moment, really fully understanding what the biosphere's role is in this, particularly as we're perturbing it to such a great extent.
I'll take further questions from the room because time is passing. There's one here. Can you bring a mic there?
How
So basic origin of CO2, where was it made of? Yeah.
Oh, I think Steve Sparks is much more suited than I to explain it.
I'm not sure about that. We know that carbon got to the Earth partly because of a certain kind of meteorite called carbonaceous chondrites, which were flying around when the Earth formed. And so the Earth absorbed some carbon, and I still think we don't fully understand the carbon, because some of it might actually be in the core. But you don't, as I think Friedhelm's shown in his wonderful talk, you don't really need much carbon, only a very tiny amount of it to enter into the atmosphere to cause all sorts of issues. So there's plenty of carbon around. Fortunately, most of it can't get out very quickly. It's deep in the earth. But as we've seen, when there are changes to the balance, then we have some real issues.
Further question? So there is one there. Can someone bring a microphone up there? It's coming.
Hello. I also want to thank Professor Blanckenburg for this great talk. I have two questions, actually. One is, you said that the surface of the Earth got more reactive, and this is the hypothesis, one of the hypotheses that you support, that the surface of the Earth got more reactive. But I want to ask you, can you consider this in conjunction with the rising of the mountains? For example, when the Himalayas rose, maybe they made the more reactive surface, the more reactive soil more available and closer to the surface that wouldn't have been if the surface didn't rise. Could you say that that also contributed, maybe the mountain ranges not increase the weathering rate, but made the more reactive soil accessible to the air? And my second question is, I know that you said the biological carbon dioxide cycle is basically closed, but could there not be a component of the biological, for example, I'm not certain, but I suppose that the plant grass evolved around 15 million years ago, some people say. And what if the grass that was so adapted to many environments of the Earth and grew so fast that this plant suddenly sucked out too many carbon dioxide, and when it was recycling, maybe even if like 2-3% of the carbon dioxide that was absorbed was trapped and couldn't go back into the cycle, and maybe this could so my question would basically be maybe there was a new species or a diversion in the biosphere that also caused the sudden sucking of the carbon dioxide from the atmosphere. Thank you.
Good question.
Yeah, thank you. These are two amazing questions. Are you a geologist? Oh, okay. Well, congratulations. I mean, the question number one, you're totally right. You can have mountain uplift and Himalayas and so on, and you have a small increase in erosion. But in these old papers, they thought increased by a factor of 10 or so. But to do this, it's enough if you have a factor of 1.5 to 1.22 increase in erosion, and then that would increase the land surface reactivity, but it could keep the weathering flux constant. And that could be made by building of mountains, yes. That is actually totally a possibility. Yeah, you're right with that. It's just a very small effect in contrast to this big mountain building and big increase in weathering hypothesis. It's a very small little change that happens. More reactivity. The other one with the grasses, I'm not such a big grass expert. The thing, I mean, I don't know what, this is maybe not what you think what I suggest. Sorry. I know there was the expansion of C4 grasses in exactly during that period. But actually, it's unclear, at least to me, whether that really impacted CO2 budgets or whether it was the other way around, that the changing climate triggered the spread of C4 grasses. The thing is, if you have a different biosphere, it does not necessarily mean that you increase carbon withdrawal, because let's say, the grass that is growing is also reoxidizes and re-releases its CO2 to the atmosphere. So if the organic carbon cycle, the biology should affect the atmospheric budget, you need to put that carbon into somewhere where it cannot escape anymore. And I don't think that grasses do this. But maybe you're better suited to answer that.
No, it's not the grass. I think that was a good question that woke me up on that. The ocean, right, is 3/4 of the Earth. And it could go in, you could get with the different phytoplankton, right? That's over half of our oxygen. So if the phytoplankton change, that's the seagrass, or sea plants. So I'm wondering if that would be more likely, I think, than terrestrial. But do they know? I'm just curious. I actually, to say, his question made me think about that, because I think phytoplankton could, because then it goes in, right, and then it can get eaten up and fall to the ocean. That would be an easy way to pull more CO2 out. So do you know?
No, that does happen. I mean, because the largest carbon cycle is are these 90 billion tons going into the marine biosphere, and but now you need to preserve them. I mean, even today, I think 99.99% of this goes back to the atmosphere, because by the time, or I don't know the exact number, maybe it's...
I think it gets to his point, we don't know.
But what you have to do is a geologic condition. You have to put this into somewhere where the carbon rains into a sediment and is immediately covered by other stuff that also rains down, like clays or so, that come from the continents. So typically, geologically speaking, what you need is a shallow marine basin close to a continent, where you have a lot of organic carbon raining down to the sediment, and you have a lot of sediment burying this carbon before it can re-escape to the atmosphere. And this is how you form oil and coal, and, well, coal not so much, but gas, mainly natural gas. So these are geologic conditions that you need, and then you increase the CO2 extraction from the atmosphere with a basin, a sedimentary basin is the word.
With regard to time, I will take one very last question, if there is one.
Do you agree?
Yes, at the very back. Yeah.
Thank you. In your explanation of the equilibrium, when you mentioned the absorption of CO2 by the sea, how does the concept of ocean acidification come and maybe contradict your theory?
Ilker or Kim? Ocean acidification?
No, I mean, maybe I'll begin with a reply, because I'm not sure exactly what the question is, but ocean acidification means you put more carbonic acid into the ocean, for example. Yeah. But the weathering process, what the weathering process does, it neutralizes this acidification by putting also more calcium and magnesium into the ocean, which we call alkalinity. So it's the neutralization of that acid. And as long as something we call alkalinity balance is always balanced, then ocean acidification doesn't happen. Only if you put more CO2 than you put calcium magnesium to the ocean, then you get acidification. At least that is my long-term answer to your question, but I bet the short-term answer is different.
Is there one? Yeah.
I mean, just a sort of comment relates to that. Again, it goes back to the biosphere. I mean, one thing we seem to be seeing with global warming and possibly acidification is stresses on the coral reefs. They're sucking CO2 out of the atmosphere, and it's clear that there's damage being done to the coral reefs. So it's an example of a feedback, because if the corals all go, then we've got one less group of species, as it were, sucking CO2 out of the atmosphere. So these things are all interrelated through these feedbacks. And I guess the struggle for Earth scientists is to try and understand the huge number of sort of interacting feedbacks with different timescales and how they work together.
And I think that's a beautiful conclusion to that discussion. I'm really fascinated by this discussion, just driven by the curiosity to understand the planet we live on. So I just propose a big round of applause for Mr. von Blanckenburg tonight and the speakers. Please stay. Voilà, cette discussion va se poursuivre dès demain soir avec la présentation de Stephen Sparks sur les volcans. Il me reste à vous dire quelques petites choses. D'abord, à remercier toute l'équipe de la Fondation Wright, Thierry Courvoisier, l'Université de Genève, Sébastien Casteltor, Fanen Sisban, toute l'équipe pour la préparation de cette soirée. Deux choses encore, chaque jour, vous le savez, des présentations sont faites juste avant le colloque par l'équipe du Sciencescope de l'Université de Genève, donc des exemples de vulgarisation scientifique de divers phénomènes liés aux thématiques de ce colloque, d'une part, et d'autre part, le fameux spectacle Son et Lumière, dont on devrait voir quelques images à l'instant. Donc tous les soirs, jusqu'au 20 novembre, si vous ne l'avez pas encore vu, allez le voir. Cette année, c'est au musée d'art et d'histoire, pas au Parc des Bastions, au musée d'art et d'histoire, tous les soirs à 18h30, 19h30, 20h30, ça dure 20 minutes, c'est gratuit, allez-y, ça vaut la peine et c'est magnifique. Donc je vous donne rendez-vous demain soir pour d'autres conférences, celle de Stephen Sparks ou plus tard cette semaine, et je vous souhaite une merveilleuse soirée. Merci, au revoir.